This is the original title, Robust Weak Values, but I was debating and I wanted to change it. And then I decided, let's put the second title here. Maybe I want to call the main topic here, it's deterministic weak value. And mainly the work will be, I will talk about several experiments, but really all around weak values. We had several, Yakir gave of course, his original view about weak values, and you know me, I like to disagree. So I'm looking for all possible ways to see it in a slightly different way. And in the beginning, I will kind of briefly mention our collaboration, which includes several disagreements. But then I will kind of make again another tutorial quantum measurements. And then I will talk about single-click measurements, which are kind of somewhat unusual for weak measurement. And one of the weak measurements will be single-click measurement. This is what's called really robust weak measurement. And this is also about protective measurement, which we also did together, which maybe now we not completely agree about the interpretation. A little about elements of reality, which is, this is the deterministic part of the story. And lately I'm like so much my nested interferometer, so I found some connection, and I will mention it too. Okay, so let me maybe start. I don't know how. I suppose I don't know if I was supposed to do this or not, but this is a list of publications from. And then I put Yakira Aronov there, and you see how many in my list of publication. Yakira Aronov is a collaborator. Of course, there is no symmetry, but also I believe that I have collaborated with more papers with you than anyone else here. No question. In my case, I think like 40% of papers are with you, and it's different.
You may be right.
Okay, and in fact, I think when we look on the papers which I wrote, I think it's even more than papers which your name appears there. Because lately I became involved in several experiments which are about works we theoretically did together. So at least 50% of my work, I think, I own you, and probably more. So thank you. And this is in fact my first paper, essentially, with you, 86. And I want to mention that the experiment was done relatively recently. About this non-local measurement in China, this is one of the latest papers with you. There is one more, but maybe less important. This is about interaction-free measurement. This was just 4 years ago, and I just got a nice message 2 days ago that the experimental paper on this experiment was accepted, and also helped thanks to Justin, who took part in this work. But really, the works which I want to talk about is this weak value, and this is the main paper about weak value AAV, and in this paper. We have a measuring procedure for post-selected ensembles of quantum systems, defines a new kind of value for a quantum variable, which we call the weak value. And in this paper, and there was some reviews after it, the weak value is presented as an outcome of weak measurement, and this is exactly how Yakir presented it yesterday. Lately, I want to think about slightly different. It's not that we all get about quantum mechanics, so it's somewhat about interpretation. So I have this paper in which I say that weak value is weak value of an observer is a robust property of a single pre- and post-selected quantum system rather than a statistical property. So I want to say that weak value is a property of a single system. So this is kind of our disagreement. I want to believe that everything, quantum mechanics, quantum state, describe single system, which I'm not absolutely sure, but I understand that Yakir prefer to talk about that quantum, definitely about Schrödinger quantum state, maybe better not to talk about. I think Yakir wants Heisenberg, and definitely probably for an ensemble. So this is our disagreement. This weak value is a property of a single system of an ensemble. I hope that discussion will slightly help to clarify this question. So let's just, although everyone knows what weak value is and what's two-state vector formalism, we have quantum state, which we all know starts going forward in time, but then measurement in the future sends quantum state which is going backward in time. And they claim that in the intermediate time, everything described by the pair of the two-state vector, psi and phi. And there is a symmetry, complete symmetry. And this is done by Yakir and Bergman and Levitch in 1964. Then I came to work with Yakir and did my PhD. And Dave Albert was a postdoc at that time or shortly before. And then Yakir came with this great idea. What will happen if now measurement will be very weak? So both psi and phi will be actual during the whole period of time. And so we got this weak value as a result of standard quantum measurement with weakened coupling. And these are these two other papers, which I'm trying to say that the weak value is really even, it's not, you don't have to talk about weak measurement. If you have pre and post selected system, I believe that every moment, if it's completely pre and post selected, weak value is a real property, more or less like eigenvalue of a quantum pre and post selected system. Okay, but let's start with the first view about weak value as a result of measurement. So let's talk about quantum measurement. Let's say we have an eigenvalue, some variable, and it's equal 1. And we use von Neumann Hamiltonian and measuring device. We have a pointer, and if integral of g of t is equal 1, then during the interaction, this pointer will move just from 0 to 1. Originally it shows it's ready, it shows 0, and after the measurement it shows 1. And okay, we cannot have exact pointer at 0. We model it by Gaussian, a narrow Gaussian. But the problem is when it's narrow Gaussian and our pointer variable, then the Q is very precise, so P should be very imprecise, so it's very uncertain and maybe it has large uncertainty. So Hamiltonian is really big. So our measurement is not, will destroy the system. So this is strong measurement. If I want to make weak measurement, then I want to make the coupling should be very small. If Hamiltonian is small, then nothing will happen to a system, not forward in time, not backward in time. Yakir yesterday presented it like putting g of t very small. That doesn't make much difference. I prefer not to touch Hamiltonian of the measuring device, to leave it as is. I would prefer just to play with the initial state of my measuring device. I want to make Hamiltonian very small, not by changing the form of Hamiltonian, but making this p very small. Very small, and it should be So p is around 0, no problem to make expectation value of p 0, but I also want to make p small all the time. So I need the uncertainty of p small around 0. But when I do this, then of course q will be highly uncertain. So the pointer, if before it was kind of showing a very narrow point, now the initial state of the pointer is spread out. So even without doing any kind of measurement, it can give all kind of results. But the evolution is the same. Our pointer shifts again by just the same value 1 if we operate it. So Hamiltonian is small, action is the same, but the pointer is not good. It's just very large. However, even with this bad pointer, we can make our measurement. If we have a system with eigenvalue 1, we can perform the experiment, look on the pointer to find it here, and then to repeat it again. We have to repeat again. We have to a new pointer, new time, new measurement. It's again measured, get another value, then get many values, and make a statistics, and then the center expectation value of the pointer after the experiment, which we will find on a measurement of the point of many pointers on an ensemble, will give us this weak value. So the weak value, the eigenvalue is a weak value. And so our measurement, the weak value is a kind of good property. If the system described by eigenvalue, the weak value will be the same. Now, if we have a superposition, the superposition, let's say 2 eigenvalues, 0 and 2, and equal superposition, then usually what we can associate to this system, expectation value. The meaning, we perform many measurements, we get some statistics, once 2, sometimes 0, make many measurements, and n2 for 2s and n0 for 0s, measure probability of each one, and then if it's equal superposition, then expectation value is 1. So to find expectation value, we perform standard von Neumann measurement, find eigenvalues, make statistics, and find now. So this is kind of this is really what happened on every measurement. After every measurement with good measuring device, the device will tell us if it's 0 or 2, because we have very well localized pointer. So it will be somewhere here, and after this statistic we can find 1. But now if we'll do the same story with weak measurement. So the same Hamiltonian, everything the same, but the pointer is very wide. Every time, what will happen with the pointer? It will do in superposition. So it will be mixture. After the experiment, we'll have this mixture shifted and eigenvalue 2 and not shifted with eigenvalue 0. And on this pointer, we can look on it and we'll get some outcome, and we'll make it many times. And average of this mixed pointer will be again 1. So it will give us the expectation value. So if it gives us the expectation value, the weak value, expectation value, I think we put it in our PRA as saying that, oh, weak value is a good concept because when weak measurement is a good concept. When we perform weak measurement on a system which is described by expectation value, we'll get expectation value. And usually experimentalists say that expectation value, this is the right description of our system. So the surprise, of course, of all this work is that if we add post-selection, so here we have another example. Again, the same measuring device, but we have pre and post selection of 0 and 2 in particular, and I choose some particular amplitudes for pre and post selection, such that in fact the weak value is what's called anomalous. It's outside the range of the eigenvalues. It's 0 and 2, but the weak value, if you take these two states, they're pretty much close to be orthogonal. Here there is a minus. And now if we'll perform the same operation with the post-selection. So the first thing, we perform the measurement, we perform coupling, and we create mixture. And when we have this mixture, still, essentially, the pointer will show somewhere between 0 and 1. This is our mixture, and if you look on it, it will be some number around, in fact, probably very close to 1, between 0 and 2. And, but when we make post-selection, then interference of these two wave function can give us something very similar and far away. In this case, it will give us 11. So, and this is our pointer again. One measurement will tell us very little because it can show all kinds of numbers. But if we'll make many of them, and then in the end of the day, we will find where the pointer shows, and it will show where we expect it, where we want to show. It will give us the weak value, which is 11. Okay, so this is kind of summary of the cases. We have, if we have eigenvalue, expectation value, or we have pre and post selection, which correspond to weak value. In all these cases, weak value is an outcome of weak measurement. So this works very well. And so the weak measurement, but the weak measurement requires an ensemble. And if it requires an ensemble, so it's really a property of an ensemble. One can say all system and ensemble are identical, so I want to associate it with one. But maybe it's not very strong argument. You may not. With one, you cannot see it. If you cannot see it, so probably it's not a property of a single system. Here's you need an ensemble.
Sorry, Ned.
Yes.
Do you mean an ensemble of measurements? In other words, you need to make a whole series of measurements, or do you mean you actually need an ensemble of systems?
Ensemble of system. Every time I have to make a measurement on a new system. There is no meaning. I cannot have one system which I claim it's pre and post selected. I cannot make many weak measurements on one pre and post selected system. Will be a strong measurement. It will give me only eigenvalues. I need new ensemble of pre and post selected system. I cannot do it with one system.
You could surely, don't want to hijack this, but you could surely make a sequence of weak
But it's the same. It doesn't matter.
System that is
but
pre-selected, and then do the post-selection after n weak measurements.
I have a pre-selected system. I have pre-selected system. I have weak coupling. I have post-selection. Yeah. Then I have my measuring device pointer. This pointer is not good enough. It's uncertain. Its center expectation value of pointer shows me weak value, but I cannot find it from one experiment. So I have to repeat the experiment. To repeat the experiment, I need that somebody will give me another system.
But we won't get the weak value.
What?
But there's no reason why you
What?
can't have.
It will be this mess.
Well, if they are truly weak, then it shouldn't be too much of a mess.
No. If they are truly weak, I'll get very, very little information, so it will not help. If they're truly weak, I can do another one weak, but some of them will not be good enough. I need many systems.
Why can't you repeat the same measurement on the same system?
What?
Why can't you repeat the same protocol on the same system? Why do you need
I have to prepare it and post-select. So this is, but it doesn't matter. Maybe if I do it in different times, it's a new experiment. It doesn't matter if I do one after the other, pre-week post, or I have many in a row on all of them pre and post. This is the same story. So I need an ensemble in time, ensemble in space, ensemble. And I want to say, no, I don't need an ensemble. I think it's a property of one system.
I have a very different question. Everything you're saying, and everything I've read about weak measurements is tied to the von Neumann model measuring device.
So wait.
And that's only one.
So wait. This is exactly what I want to go out.
Okay.
Yeah. So this is also, there is essentially one review written by people from here. And this review has the same approach, weak value, conditioned average of generalized observable eigenvalues. with slightly different name, but essentially the message is the same. Weak value is conditional expectation value on post-selection. But there are more experiments which I've been involved on works with Yakir. And one of them is protective measurement. And again, this was relatively long time ago, this work, not very long. More or less the same. And the experiment was done relatively recently in an Italian group. And Ellie was taking part. You are here. And here it's essentially the same experiment presented slightly more in detail just very recently. In this experiment, essentially, even if we read the paper with Yakir, we show that it is possible to measure the Schrödinger wave of a single quantum system. This provides a strong argument for associating a physical reality with a quantum state of a single system, and challenges the usual assumption that the quantum state of the physical has physical meaning only for ensemble of identical system. It's written by Yakir, signed by Yakir and me, but as I understand Yakir, you want to distance yourself from this. What? Okay, so let's briefly describe the story. How we measure this protective measurement. Roughly, we put a protection so it cannot really change, and then we perform many weak measurements on different operators. And if this, when we have all different expectation values, we can reconstruct our wave function. So really the result, that expectation value, and this was a paper which is kind of strange paper. Expectation value is a statistical thing. But if the system is protected, we can find it on a single measurement, single click measurement.
Can you say a word about how you protect? How you protect action?
There are two kinds of protection. It's either it's a kind of eigenstate of energy with a gap, and then you have to make weak adiabatic coupling in your measurement. Or another method which you used here, it's a xenoprotection. So one person make a measurement, another person who knows the state test every time that this remains the same state. And the idea is that you still get information because you don't know what the other person who make protection, the xenoprotection. This is what happened in this example. Somebody tests that the state remains the same during your measurement. You couple to it, so it remains in the same state because Zeno effect tells that it cannot run out. Your measurement doesn't. If it's long enough, it becomes strong, and you know the result. But the protection, Zeno protection, keeps it the same. So here we talk about polarization again. The measurement experiment which I've been involved, only optics, polarization, and we have polarization operator, one for H minus one for V, and we have particular expectation value for it. This is theoretical. And in Italy, there was kind of array of single photon detectors. Then every square is really a single photon detector. And then we start open it, and they start clicking. And so this is we count how many click around -1 and how many click around +1. And then we make statistics. Out of this 20, we get not too far from our expectation value. And so this is just a test of the system. Then we took the same system and added the protection. We added the protection, and we sent a single photon, and it came not too far from our expectation value. A single click. Send the photon on this protected system, we get this click, and not too far from the expectation value, statistical value by single click measurement. kind of, there were really many, it was many birefringent crystals. This is how we do, and when we send a wide beam, and the polarization, H polarization go to the left, it's conceptual thing. But this is really, the picture of the screen is more or less exact. And the plus one go to the right, and this without protection, and this is with protection. So without protection, we will get something either on the left or on the right. With protection, you get something around expectation value. And again, the precision, it's about the width of this beam. It doesn't change significantly. This is how I probably can use.
That's got my germs on it. I love this conversation.
Thank you. Thank you. So this was just the test which we did, just to see that this single click means. Because you see, without protection, many photons which we got this picture, double picture, and well, with protection it gets this one. We were kind of lucky. This is our first one. It was not too far from the center. And this tells us the accuracy of this single measure. Okay, then another experiment. A robust weak measurement, the same with the same group, essentially the same kind of machine, everything the same, but we added pre and post selection. We wanted weak measurement. And in fact, this is also essentially this experiment is the first realization of weak measurement paper, which weak values. I'm not sure the word weak value was there, but the idea was there and the story is there. But it was really for a special case. It's kind of rare quantum event. It was also done the main kind of famous paper AAV, and this is AACV because Ron Kasher took part in it. So it's measurement of weak value, again, of a special variable. If there are some special variables which are sum of other variables, then the weak measurement doesn't have to be very weak to get very well a good weak value from a single click. So again, the same kind of story. This is kind of interpretation. First, in a protective measurement, all this protection was the same. Now they are not the same. One state, another state. One state, another state. So the coupling, the measuring device was really a transversal degree of freedom of our photon. So it's coupled in different times. So this is kind of sequential discussion. If I sequential measurement or in the same time measurement is kind of the same. So I claim the same story if we measure in different times or we measure 7 photons. So this is the variable is really the sum of photon polarization at seven different times, which is kind of equivalent to sum of polarization of 7 photons. They all pre and post selected in the same state. One it's psi-phi, and now it's post-pre, but if it's real, it doesn't matter. So the weak value is the same if it's psi-phi or phi-psi. And the weak value was arranged so it will be anomalous. Each one is between -1 and +1 polarization operator, 7 between -7 and +7. But here the 7, so that the total of 7, maximum 7, but here it was 18. And this is the click we got. This far away, I think it was about slightly more. Single click measurement, 21. We add with precision, which much better than this. In fact, I have here again. In our language, you remember this weak measurement. Our pointer wasn't so wide. This is our pointer for measurement of this variable, which is supposed to get 7. This is our pre-selection state, post-selection state, this weak value. There is some fine-tuning I will not talk about, why it's really 18 and not 20.5, which you use the formula. After the coupling, they move. If it's all pluses, so they move 7 to the right. If they're all minus, they move 7 to the right. So we started with the pointer like this, and this pointer was coupled to all of them, so it started to be wider. But again, this is more or less how it looks. After the post-selection, it was far away. So this is our robust, we get anomalous weak value with a single click. If the pointer is here, so of course a single click probably will be somewhere here, and it was in fact here, 21. And then this is kind of a statistic which we did to test it. If we did it many times, and this was a histogram of all of them. So anomalous weak value is a property of a single pre- and post-selected system. So if I look on this experiment, then I can say, oh, a single click measurement describes single system. It's clear, it's true that I have to prepare maybe many of them, but I don't, and only, this is rare quantum events. To get this particular click, it was rare. But I don't care. In this case, when I have a single system which was pre and post selected. And I claim that my weak value belongs to this one. So weak value is a property of a single system. Then, and the expectation value is a property of a single system. This was a previous experiment. But all kind of question. It really was protected one. So maybe it's a property of protection and not on the system. And our weak value, it wasn't so exact. I said I got 21 or 18, but it was plus minus 5 or 7, I don't remember. So this is kind of approximate, maybe. And now, if I have these other cases, this is if I don't have special operator, we will not get single click weak measurement. So in normal case, sigma x equals 100. It cannot be done in any way with a single click. So, and expectation value is clearly statistical story. How? So, I want to change slightly the approach. Like, I want to say that the weak value is really a property at particular moment of time of system which is pre and post selected. There is a pre-selection at particular times. The psi go from past, phi go from future, and I claim that if I have coupling for very short time to a particular variable here, c, never mind of this kind. So this is my total Hamiltonian. C times I coupled to C, and B it's everything else. Then the claim is that really that's effective coupling to a C number, this weak value of C. And the weak value is given by the standard formula.
Which is the quantum, which is the pointer?
Wait. So the C is my variable in my system. B is everything else. It may be measuring device, it may be environment, it may be everything. And then C is pre and post selected. My system is pre and post selected. So I know it's pre-selected in psi, post-selected in phi. And here, and I look, chi is a property of everything else. So I say that everything else really fills this Hamiltonian with this C number. This is chi is a property of the whole universe coupled to my system before and after. And I say that it couples as if the Hamiltonian is like this. And again, there is this is initial state, my system psi, environment chi. This is a coupling due to this Hamiltonian. I make post-selection, and so this is my state after. I can standard kind of weak value computation give me this. If I look on Hamiltonian measurement type of Hamiltonian, so Yakir suggested to make G very small. Before I suggested to make P very small. Now I suggest don't touch anything, don't do anything very small, maybe even big. I want to consider very tiny time of this Hamiltonian. And the claim is I want to see how my system all environment, it should be not entangled. Of course, I have my system in psi, my system later in phi. They are not entangled with the system. And this is everything else. Everything else will change from chi to chi by t plus dt. And this change is characterized by the weak value of my system. So if I look on our measuring device here, and maybe just to make this very short time. So you see, and I want to look in this new language, not outcome of a measuring device. I say that any coupling of a system described by two-state vector for a short time is a coupling to the weak value. Then just consider it tiny, very tiny time. So it shifted like this. I had Gaussian around 0. Now it shifted infinitesimally to the right, according to number 1. Here, it's really shifted also infinitesimally, but times 11, more or less. Here, it's became mixture. If I couple to a superposition, then it's mixture. So what I want to say is that this one does not fit my definition. If I have coupling of my system which is not post-selected, after my coupling, my environment is in a mixed state. I cannot say that my environment was coupled to some C number. If it's coupled to C number, it will remain pure state. But now it's mixed state. So here it's okay because it's after post-selection environment again in a pure state. And moreover, when epsilon goes to 0, that dt go to 0, this looks like coupling to an eigenvalue 11. Even if there is such a thing. If I have eigenvalue to 11 and move like this, and this wave function in the limit exactly the same. Pure state and the pure state as eigenvalue. Eigenvalue and weak value, coupling to eigenvalue, coupling to weak value in the limit of very short time, it's the same. Okay. So now I want to say a property corresponds to a single system if it characterized by a deterministic outcome of an experiment. What kind of deterministic outcome of experiment I want to consider? I make this very short coupling, and after this I know with probability 1 that if I will find this shifted Gaussian, I will not make measurement which I prepared, where is the pointer. No, it's Gedanken experiment testing my measuring device. Is it shifted by Gaussian, or by exactly, is it in this state? And it will tell me with probability, I know that if I will have the equipment, it will give me this result with probability 1. Now, in a sense, it's not enough to know the weak value, because maybe the weak value is different and it can by chance give me this result. So I have to repeat it many, many times. I do need the ensemble. And if always it will give me this one, I know my weak value. But what's important here, I have only measurement with deterministic outcome. It's the same like in eigenvalue or the same like here. It doesn't work for expectation value. Because after, if I couple to expectation value, I get some mixture. There is no any measurement of my environment which will give me a probability 1 when I'm in a mixture.
Just a clarification question. You're not counting the post-selection as a deterministic or non-deterministic outcome? Because to get the post-selection, of course, is also a random process.
First, nothing random. When I make a post-selection, I split the word, and in every word there will be particular post-selection. This is my philosophy. But for current discussion, in all the things, post-selection is given. So I consider the question, the weak value is not psi, a, phi, psi, phi. If there is no phi, there is nothing to talk about. You can talk about expectation value, which I think you should not, because the weak measurement will give you the same kind of number, but I think it's not good. The weak value is psi, a, phi, psi, phi. No phi, no weak value. Post-selection is given.
But it does, what it does, the point of Andrew's question is that it does affect the height of these curves there.
This is the whole point. This is after renormalization. Because if I just make superposition of these two Gaussian, I will get something very tiny. But I got the outcome. After I got the outcome in my world, I will not see any difference. It's normalized. In every world, every quantum state, every state is normalized. It has exactly the same height like here.
If you're comparing it with the value without post-selection, which I think your top middle curve is,
Yes.
is that right?
Yes.
Okay, the top one should be a much, much higher curve for true comparison. Because,
No. In my experiment, I go to laboratory, I prepare the system, I make coupling,
yeah,
and then I wait until I get the right post-selection. I got the post-selection. Now I go to compare to other experimentalists who didn't need to post-selection. He worked less. He didn't have to repeat it many times. But in the end of the day, we will talk. I with post-selection talk to him without post-selection.
but if he did repeat it
Yes.
a number of times in his laboratory, then his curve would be much, much higher than that. But then it wouldn't fit on the screen.
I don't know, but this is not. But okay, so let me. Okay, so then, so I want to talk about values. So I look to Stanford Encyclopedia of Philosophy and says if I have eigenvalue, and orthodox quantum mechanics says values only when you have eigenvalue. If you're in an eigenvalue of operator don't have values. Expectation value is statistical, which I kind of agree. And but then why I think deterministic is important. Like this EPR tell us. So this is kind of ideas from EPR. If it knows something with certainty, there is a value. The EPR elements of reality. Now I have to modify it slightly because EPR they wanted to predict. And here I'm talking about something in between measurements. So I cannot really say predict. Somebody performed my weak measurement before the post-selection. Maybe I'll look later, but it was so I have to change predict to infer. But otherwise, everything with probability 1, it's kind of elements of reality. For example, there is interesting two-state vector formulas that have important, I think, theorem. If I have pre- and post-selection such that my variable equal, such that I will get some eigenvalue with certainty. It doesn't have to be eigenvalue. Like I can have be in 3 boxes, A plus B or B plus C. Then B will come with certainty. So then the weak value should be equal to the eigenvalue. There is a theorem. Projection operator of on B will be weak value will be 1 when I know that I will get 1. Moreover, for dichotomic variables, and this is what's interesting, it works in another way. If there is some dichotomic variable and the weak value is equal eigenvalue, I know that if I perform strong measurement, I will get it with certainty. So this is in fact how, again, another work with Yakir, how we found this interesting situation about the spin half particle, and for which we can know sigma x, sigma y, and sigma z with certainty. Because if one of them is measured. Because we found particular pre- and post-selection of entangled pair of particle with something else, in which the weak value of sigma x, sigma y, and sigma z was equal 1. And then we know in this case that we'll get sigma x with certainty if measured. Sigma y with certainty is measured, and sigma z with certainty is measured. So this is kind of important theorem. Now this theorem works only for deterministic weak values. What is deterministic weak values? It's when we have complete pre- and post-selection. When we have complete pre- and post-selection, not like expectation value. The expectation value we can define weak value like outcome of a measurement, but it's not deterministic weak value. So just to exemplify it on the nested interferometer, if I have this nested interferometer, Mach-Zehnder interferometer, if in principle it can continue here and we can go, but now I arrange the inner interferometer so it's go out. If I'll send a photon there and I do nothing, then it will split equally between A, B, and C. In fact, it's A plus B and C is a quantum state. I will say that it has weak values of projection operator in every place, even now, even without post-selection, because according to the definition that the weak value is a result of weak measurement, expectation value is a weak value. So in this case, we have weak values, one search, and one search. Now, if this slightly, I don't know, maybe for me it was surprise, but for some others also surprise. If I get a click here, then we get a strange weak values. So this is not strange. It looks like it can go only from here, so that weak value here should be 1. But it turned out that we also get 1 here, and we'll get -1 here. And these are deterministic weak values. We know that if I will make a non-demolition measurement here, its projection operator is dichotomic, and it's equal to 1, which is one of the eigenvalues. So I know with certainty that I will find it here. I also know with certainty that I will find it here. -1, it's not an eigenvalue, so if I'll measure here, there is some probability in maybe 1/5 that I'll find it, but I don't have any theorem. I know here it's with certainty yes, but here I don't know. Now, why bring it? Because how it's relevant, there is this interesting case, which once I talked to Howard about this because it was puzzled for me, and he immediately understood what's going on. And here there is a strange, so instead of putting detector here, I will put a detector here. And it's 100% efficient detector, and it tells me that there is no photon. In this case, it's kind of a partial post-selection. Usually I have pre-selection and post-selection. I know exactly what's going backward. Here I know that photon does not go from here. So maybe it's from, apparently it's go from here and from here. In fact, there is something else. So in this case, I can calculate the weak value. And I will find that here it's 1, and here it's 0, and here it's 0, which is kind of natural. But these weak values are special. This one is normal. If I'll measure here, I will find it with certainty. But this one are non-deterministic. Because usually, if the weak value equal eigenvalue of dichotomic variable, it should give me the outcome with certainty. And here it's 0, and here it's 0. But here it's not true that if I'll try to find, to look for a particle here, I will not find it with certainty. Because non-demolition measurement destroys interference, and then it might not click even if I find a particle here. It's what is really going on after it. After not finding it here, I can find it here and change the story. Here, for example, when I find it here independently, it doesn't matter. This will be 1, and this will be -1. But I might not find it. And then this one will be 1, and this -1. So essentially, in this case, there is a mixture here of 1 and -1. 1 and -1. And the mixture give me, again, the mixture of 1 and -1 give me a weak value 0, like expectation value. So sometimes I have hybrid situation that the same system, one photon, pre and post, kind of partially post-selected, and then something is still deterministic, but other thing is non-deterministic. If it's completely post-selected, it's always deterministic, and this is, I think, for me, kind of, if the particle is described by the two-state vector, if this is complete post-selection, then I say that we have any coupling for infinitesimal time couples to this. It has nothing, from here, it follows that the measurement also will give me the right answer. But this is not, I don't want to take this as a definition. I want to take a definition as infinitesimal coupling to everything else. This is, of course, always true. And I don't know, I started, so clearly it looked like I'm in time because I started at like 10-15 minutes. I have maybe time for a short quiz, puzzle. Well, what is the time difference between these two pictures? somehow this was done a few months ago in a conference on IFM, and this was done in Tel Aviv few times very shortly before. This is I put in my talk in 80th birthday conference. So happy birthday, Yakir, and I wish you many more decades of research, and in particular many decades of disagreements.
The hair is a little wider on the left. That's the only difference I can see.
Well, that was just the lighting.
So, questions? Yes.
Coming back to this robust or protected measurement, your story or your idea is that you have some weak measurement, there is a back action on the system, but then due to some zero measurement, you undo this back action and you project the system back to its original state. Now, there is a competition here. On one hand, if the weak measurement becomes weaker, then the back action of the system is smaller, and you need less effort in order to get it back. On the other hand, if you want to, if the measurement is really weak, and you want to extract some information of the system to overcome the noise due to a weak measurement, you need to perform a very large number of repeated measurement. And I note that each zero measurement has some probability, exponentially small, but some probability to misbehave, to jump you to an unwanted state. So here is the interplay. I mean, you go weaker, and you need more measurements, and then the probability to make some error becomes larger. So I don't have time to calculate the balance, but what is the balance between the two?
From practical point of view, you're absolutely right. And this is why in our protective measurement, the xeno protection were only 7 times. But theoretically, if you perform xeno protection as many in infinite with a number going to infinity, the probability of an error go to 0. So theoretically, I can protect completely. I can perform standard measurements, von Neumann. Go to laboratory, Brian or somebody perform measurement. If I have super technology performing very fast xeno protection, every standard measurement will give me this. If it will give me this expectation value. So theoretically, there is no problem. In practice, because there are some, on every xeno, there is some reflection and whatever, in practice, I have to take this in account. So I should, how it, it's okay. So I think, I think Abby was before then, yes.
Could you show again your nested interferometer? So actually the story that you are telling is very interesting, and it is that actually the particle didn't go on the upper path. It didn't emerge where the detector is, right? But within that nested, for a while there was a particle.
What confused me for a while, and why I find it interesting, that if you look on the weak values, then there is a weak value in C1, which no problem, everyone agree, before, after, no question. But in this case, when I get negative result in this detector, the weak value in A and B are 0. So I would kind of say that naturally to say for me that the particle was not there. It was also 0, there is, of course, here. And here I say it was not, and clearly the story, it's not here. It was not here like in the standard, where it is. Oops, sorry. In this case, the strange thing is that it's here but not here. But in this case, not only that it's not here the weak value is also 0, but it's look like 0 here and 0 here. So usually the idea the weak value is 0, so the particle is not there. But it's not true. The particle is there. Because this is not the right language again. All kind of disagreement with Yakir, but it's semantic disagreement. For me, that the fact that my projection operator give me 0 doesn't tell me that the particle is not 0, because there is some other local operator in this region with weak value which is finite, like your smile of your cat, of Cheshire cat. And this for me, then I will name it that the particle was there. So when there is a Cheshire cat smile, I don't want to say that the particle that the cat is not there, but this is semantic. So here, the particle in B, the particle is in A, in spite of the fact that the weak values of projection are 0.
Now, there is another work which is probably known to you because it was written by you and Yakir, and this is the shutter experiment. There you showed that sometimes some predictions of the TSDF can be shown with projective measurements.
Exactly the difference. The shutter experiment was working when we have a deterministic weak values. And then the weak value 0 tell me that I will never find a particle there. Or weak value 1, I will always find a shutter and nothing will come here. And this is not deterministic weak value, which is, I think, has different, less status. This is, if I will make weak measurement, I will find the presence 0, because it will be a mixture of positive presence and negative presence. And I think it's not robust, it's not deterministic.
Right, but now there is a paper and an experimental work which synthesized both of your works and showed that in a version of the shutter experiment you can show by projective measurement, not weak measurement, that indeed there was no particle going into the nested interferometer, there was no particle going out of the nested interferometer, but for a while there was a particle within the interferometer. You probably know this work, just I want to ask you whether you like it.
Let's discuss it after.
There are two works of yours there which we synthesized and published in Nature Scientific Reports, and now there are experimental results of them. So these are not weak measurements.
There are subtleties there, which I think I don't have. It's not that I don't want to say it in public. There are two. It's too. The answer is too long.
Can you just tell us whether you like it?
It's interesting. Yeah.
I'll try to talk about it.
Yeah. Ephraim.
So I know that you like disagreement. And I was
Yes.
really
Yes.
happy enough,
Please.
So I thought I'd offer you some.
Please.
I'll begin with some agreement. I really appreciate your point about the difference between weak values and expectation values and getting a pure state for the detection. But I want to come back to this question of the protected measurements and suggest that really what you're measuring is the state or the basis of protection. You're measuring the property of those polarizers that do the Zeno projections, in the sense that if you took the incident photon and changed its polarization by a small amount, your final result would be almost insensitive to that. It's really sensitive to all of the projections you do in the middle.
I think that this is okay. First, in this protective measurement, the idea is that there is me who performs this measurement, and there is somebody else who makes the protection. Now, if he will make a protection, he give me a different state, alpha prime, beta prime, and he protests it all the time, then I will find this other state. Now, moreover, it looks like this information is already present. I can arrange maybe something, sometimes measurement you're supposed to get new information. Here I get new information which somebody else knows. I can also arrange something that no one knows. I can think, maybe not for polarization, but for some other things, I can think about protection which works for different states simultaneously. And then I will find which one of the protected states is there by my protective measurement. So this gives me some new information, absolutely new. This was the question, or I?
Yeah, no, I think that would be very interesting. If you're protecting not a single state, but a set of states, then you get information, although in a sense that would be discrete information if you don't want that to be a continuous subspace.
Yeah, yeah.
But in this particular case, you've written the same alphas and betas for the state preparation and for the protection.
Yes.
That's a built-in assumption. And we're not really learning anything about the alpha and beta at the source, but about the alpha and the beta of the protections.
I think.
Why would you disagree with me?
No, in fact, you see this protective measurement is expectation value. I think expectation value is statistical, and this measurement doesn't tell us anything about deterministic weak value because, sorry, the experiment really with xenoprotection, it's I think it's red herring to say that I measure protective expectation value. All what it is, it's all pre-selected psi, post-selected psi. So it's really a weak value. I say there is a difference between expectation value is psi, a psi. And then I can present it as weak value, psi, a psi divided by psi, psi. The second one, which is numerically equal, is deterministic and can be measured. The psi a with no future, I think it's only expectation value. It's only statistical. It doesn't have this feeling of element of reality. And in this experiment was really measured. Is this really? It was really many. It was really measurement of deterministic weak value. But it was kind of forced interpretation of the expectation value. But it's because of the numerical. But it's not really. Yakir, you don't want to make any comments? No?
I think it's mostly semantic.
Yeah.
So I don't want to discuss semantic differences.
But just my question, I don't know if I'm allowed to. You finished your talk with a claim that, look, everything is quantum mechanics, it's correct. But then the way to present it gives us new ways of thinking. So my feeling that your way of thinking is non-local, non-locality, modular variable with non-local story. It's a way of thinking allowing new questions. And I think my way of thinking allows another question. So I think all this legitimate. It's not that there is a one way which is legitimate. It's not, we do not disagree about result of measurement. We disagree about interpretation. But here's the question, is this different interpretation can lead us to a new result? I want to believe that there are many ways which can bring to new results. And that what I'm doing, I'm definitely agree that what you are doing, there is a proof that it's led to new result. And I believe that some of the results which I'm doing, which are in different directions, which also can bring to new results.
I think that if there is a situation that you tell two different stories, it's not about the same thing. It's two different stories about different things. You can't have two different stories about the same thing, and both of them will be right. So let's talk about it separately, okay?
Okay.